Thanks for the introduction and the invitation to speak. So yeah, I'll be talking about spectral minimal partitions. So, well, first off, I need to tell you what minimal partitions are. I'll talk about some of their interesting properties and some recent work that I've done with some of my collaborators, including Gregory Berkolaiko, who probably many of you know, Yaiza Canzani, Peter Kuchment, and Jeremy Marzuola. So most of the new results in this talk are joint with them. So there's some really general kind of vague motivation for the concept of a minimal partition. So without getting too specific here, there are lots of applied examples in math, physics, biology that involve taking some planar domain or maybe a manifold or a quantum graph, partitioning it into a bunch of disjoint open sets, calculating some sort of energy functional for that partition, and then trying to optimize over all partitions of the domain. So I'll give a concrete example in a few slides when I actually define a minimal partition, but these are some historical examples. So this idea first arose, as far as I know, in the study of two-phase free boundary problems by Alt, Caffarelli, and Friedman, reaction diffusion systems with in the strong competition limit where you have multiple species competing for physical space. In certain limits, you see this segregation where they tend to localize or cluster in disjoint regions. More recently, kind of more relevant for this talk, looking at nodal domains of eigenfunctions of the Laplacian. That's another example of partitioning a domain in a kind of geometrically natural way. And a final fairly recent example, looking at multi-component Bose-Einstein condensate, so the Gross-Pideevsky equation. Again, I'm not going to elaborate on any of these except for the third point about nodal domains of eigenfunctions, but this is some of the background and history where these ideas arose from. Okay, so what is a minimal partition? What do we know about them? Why do we care? And what is still unknown? Okay, before I go on, here's some nice pictures I'm sure you've all seen. These famous Chladni figures. So this is just these show different partitions of the disk into disconnected components by the nodal lines of eigenfunctions for the Laplacian. So what is a partition? Well, I'm going to start off with some planar domain omega. I could also take a compact manifold as well. That's fine. I'm going to assume two dimensions, though, for simplicity. So planar domain, let's say piecewise smooth boundary. And by partition, I just mean some disjoint collection of open sets in my domain omega. So here's a couple examples. And I'll say that one of these partitions is bipartite if it can be two colored. So each component can be colored, say, red or blue, so that neighbors always have different colors. So the one on the left is bipartite. The one on the right is not because of these triple junctions where I have three domains meeting at a single point. So an important example of a partition is if I take an eigenfunction for the Laplacian on my domain omega and look at its nodal domains, those are just the connected sets where my eigenfunction is non-zero, so either strictly positive or strictly negative. So those partition my domain into disjoint open sets. And on the interface between two of these sets, so if I have a zero for my eigenfunction along some curve, it has to change sign going across that curve. I can't have two positive nodal domains adjacent, otherwise that would violate unique continuation. So an eigenfunction always changes sign across its zero set, which means this nodal partition coming from an eigenfunction is necessarily bipartite. So those are partitions. What is the minimal part here? Well, for each partition, I'm going to define this energy functional lambda of p as follows. So for each subdomain omega I in the partition, I calculate the first eigenvalue of the Laplacian with Dirichlet boundary conditions. So I do that for each of my k subdomains. And then I take the maximum of all of those and define that to be the energy of this partition lambda of p. And maybe I'll mention just in passing that there are variations of this that show up in literature. So another one that shows up quite frequently is basically the LP norm of these eigenvalues of the subdomains. So you just take the first Dirichlet eigenvalue on each subdomain and sum up the p powers. There's some normalization, doesn't really matter. So this is another kind of energy functional for a partition. The one that I'm looking at, this maximum one, is just the limit of this as p goes to infinity. Okay, so what is a minimal partition? Well, I'll actually define it in the next slide, but it's probably exactly what you would guess. It's a K partition, so partition into K components, that minimizes this energy compared to all other K partitions. But what I want to focus on in this talk is kind of three different notions of minimization that one might occur. So first, we can talk about global minimizers, which is just the usual sense of minimizing. I can talk about local minimizers, so getting more into calculus of variations and Morse theory. And then there's also this notion of topological minimizers, which I'll define later on in my talk. And so kind of the main thing that I want to communicate is what are these three different notions of minimization for spectral partitions, so global, local, and topological, and how are these things related, or how are they different? Okay, so global minima, well, it's exactly what you would think. I have a K partition, and I say it's minimal if it has energy less than or equal to any other K partition of my same domain, omega. And this is completely obvious, but maybe just to emphasize for later reference that all I need for this definition is to know what a partition is and what the energy of the partition is. I don't need any kind of structure on the space of partitions. I don't need any topology or metric structure or anything. It's just a function defined on a set. I can talk about a maximum, no problem. Later on, I'll have to introduce further structure to the set of all partitions of my domain. Okay, so this is a minimal partition. What do we know about these? Well, it's been shown by a number of people, hopefully all listed here, that for any integer k, a minimal k partition exists. So we've got existence theory. There's nice regularity theory as well. Essentially, what you can show is that the boundary set of the partition, so the boundary of each of the subdomains, consists of piecewise smooth curves, and whenever they intersect, they have to do so at equal angles. So, I mean, this is not actually a minimal partition, but this is the kind of regularity that we're guaranteed. So piecewise smooth curves meeting at equal angles, exactly as happens for eigenfunctions of the Laplacian, right? Their zero sets have this exact same geometric structure. Okay, so that's existence and regularity. Well, maybe more interesting, can we actually calculate or characterize any of these? And the first big result in this direction from 2009 by Helfer, Hoffman, Ostenhoff, and Terracini says that in the bipartite case, so this is a partition that can be two-colored, red and blue or plus or minus, it's going to be minimal if and only if it's the nodal partition of a Laplacian eigenfunction, and that eigenfunction is Courant-Sharp. So I didn't write it on the slide, so maybe I'll tell you what I mean by Courant-Sharp here. So I've got my domain omega. I'm looking at my eigenfunctions for the Laplacian. I'm going to assume Dirichlet boundary conditions on the external boundary of my domain. I'll order the eigenvalues in increasing order, so lambda 1, lambda 2, lambda 3, etc. In increasing order, repeated according to their multiplicity. So with this labeling convention, there's a really nice theorem due to Courant, the nodal domain theorem, which says the nth eigenfunction, psi n, again, with this ordering, has at most n nodal domains. So its zero set divides up our domain into at most n connected components. A good comparison is Sturm-Liouville theory for ODEs in one dimension. The nth eigenfunction has n minus 1 zeros, so it divides up the interval into exactly n nodal domains. So in one dimension, we have equality, psi n has exactly n nodal domains. In 2 dimensions or higher, we just get an upper bound. There's at most n nodal domains for the nth eigenfunction. Okay, what is a Courant-Sharp eigenfunction? It's just an eigenfunction that achieves this upper bound. So I'll say the nth eigenfunction psi n is Courant-Sharp if it has exactly n nodal domains. So what this theorem tells us is, so we look at the nth eigenfunction, it has some number of nodal domains. If it saturates that upper bound, it has exactly n, then the nodal partition of this eigenfunction is actually a minimal partition, and vice versa. Every bipartite minimal partition arises in this way, as the nodal partition of some Courant-Sharp eigenfunction. So on the one hand, this is great. It tells us exactly what all of the bipartite minimal partitions look like, as long as we can understand the corresponding Laplacian eigenfunctions. So on the one hand, that's positive, but there's a negative side to it as well. If our goal is to understand minimal partitions for arbitrary values of k, there's a really nice theorem due to Pleyel from the 50s, which says on any given domain, there can only be a finite number of Courant-Sharp eigenfunctions. So psi n is only Courant-Sharp for finitely many values of n. So for instance, the first eigenfunction is always Courant-Sharp. The second eigenfunction always is. Beyond that, it may or may not be. But no matter what our geometry is, beyond some finite value of n, we're always going to have a strict inequality here. And so what that means is almost all eigenfunctions are not Courant-Sharp, which means most minimal partitions do not arise in this way. So they're not bipartite. And so if we want to understand all minimal partitions, not just the bipartite ones, we need to somehow move away from the Laplacian. And to give you an idea of how subtle this problem is, let's look at arguably the 2 simplest planar domains, the disk and the square. In both of these cases, we know exactly what the bipartite minimal partitions are, because those come from the Courant-Sharp Laplacian eigenfunctions, which can be characterized. So here's the minimal 1 partition for the disk. It's just the disk. Minimal 2 partition, you just divide it into 2 pieces. There's a whole 1-parameter family of minima by the rotational symmetry. Dividing it into 4 pieces gives the minimal 4 partition, and similar pictures for the square. Interestingly, though, if you look at k equals 3, it's not hard to show that the minimal 3 partition for the disk cannot be it cannot be bipartite. So it's not coming from an eigenfunction of the Laplacian. And so a very natural conjecture is that the minimal 3 partition of the disk is this so-called Mercedes star partition that I've drawn here. But this is still not completely resolved. There are partial results saying, with some a priori assumptions on the structure of the minimizer, if you assume it only has one singular point where the nodal lines meet, then it has to be that. But there is still no complete proof that that is the minimal 3 partition of the disk. And likewise for partitions of the square. So even in the simplest possible cases for small values of k, it's very difficult to completely characterize these minimal partitions. Okay, so that's kind of a general overview of global minima, or just minimal partitions. Now I want to talk about the local theory more. And this is getting into stuff that Greg and I have worked on together. Well, another obvious statement, if I want to talk about local minima, well, I need to know what I mean by local. So I need some structure on the space of partitions. I need some topology at the very least. But really what I want to do is calculus, right? I want to do first and second derivative tests to find local minima, saddle points, et cetera. And so I need some geometry, meaning I need some kind of manifold structure on this space of all partitions of my domain, so I can then deform my partitions and calculate derivatives. So I'm going to start off by looking at the simpler case of what's called a smooth partition. So this is one where the boundary set or nodal lines are just a bunch of smooth curves. Maybe they intersect the boundary, but if they do so transversely. So here's a 3 partition of the square. And in this case, right, I can just pick a normal vector on each component of my boundary set. And then any deformation of this is just parameterized by some smooth function on that boundary. It just tells me how much to move in the normal direction, like in this picture here. So in this case, we can say, at least in a neighborhood of P, that's this partition, the set of nearby partitions is parameterized by some suitable function space, say some Sobolev space of functions on the boundary. That gives you a local Hilbert manifold structure. You can do first and second variations. However, if you have intersections in your nodal set, say in this picture here, that doesn't work because now, say at this point here, what is the unit normal to the boundary set? It's not well defined. So I can't just fix a normal vector on the boundary and say deform by a fixed amount in the normal direction. Something weird is happening here that I need to take into account. So how am I going to parameterize deformations in this case when I allow intersections? Well, first off, I should tell you what kind of intersections I'm actually allowing. So the objects we're looking at are called partitions with corners. So this is a partition of my domain omega with the property that each component omega I has piecewise smooth boundary. So this one here would satisfy that condition. And I'm also going to assume that all of the corners are convex. So I can't have too wide interior angles on any of the corners. Might seem like a weird assumption. We need it for some elliptic regularity, kind of boundary regularity results to apply. It ends up not being a big deal because it's known that minimal partitions have these nodal lines meeting at equal angles. And so we're not going to have interior angles bigger than pi anyway. So for the consideration of minimal partitions, this is really not an extra assumption. So what I'm going to do, instead of thinking about just deforming this boundary set in the normal direction, I'm just going to take some diffeomorphism, mapping my domain omega to itself, and then just deform the entire partition. So I just map each component of the partition under this diffeomorphism. That gives me a new partition where everything is just shifted by some amount. And now what I'm going to do is view this energy functional lambda as a function not on the space of partitions, but on the space of diffeomorphisms. And this is nice because the space of diffeomorphisms has a nice manifold structure that's understood. And so then we can do calculus there. So what I do is fix some reference partition P, like I've drawn here, apply my diffeomorphism, that'll give me some new partition, and I calculate the energy of that. So that's the energy of this diffeomorphism P. So that ends up being a natural way of parameterizing things when we allow for corners. But an interesting thing happens. So if I look at these 2 partitions I've drawn here, so one I'm just partitioning into 4 pieces with these 2 lines. On the other hand, this partition here, this intersection has split up into two triple intersections. And so these are not related in any nice way, right? There's no diffeomorphism on the square that maps this partition to this partition. And so if I look at my energy functional, if I calculate the Hessian of that, so I calculate the second derivative to see if I have a minimum or not by comparing it to nearby partitions, well, my energy functional, and hence the Hessian of my energy functional, is not going to see this partition because it's not a smooth deformation of this one. And it seems like that might be a problem, because what if there is a partition like the one on the right, which in some heuristic sense appears to be nearby this? What if there is a partition like that that actually has lower energy? The Hessian, it seems like, would not detect that, because this is just not in the allowable space of deformations. However, something really interesting happens here. Even though the partition on the right is not the image of the one on the left by any diffeomorphism, it can be approximated by partitions that are diffeomorphic to the one on the left. And so the picture, I'll try my best to draw it over here, is something like the following. So I take the partition on the left, I can find a diffeomorphism that it basically pinches the nodal lines together near the origin. So I have something like that, and then similarly in the other direction. Now, this is a smooth deformation of the partition on the left, and in, again, some vague sense that I'm not going to make precise, this is sort of getting close to the one on the right, even though it's not actually converging in the sense of diffeomorphisms, because these diffeomorphisms are going to degenerate as these lines get closer and closer together and stop being invertible at some point. But the point is, so even though we don't get these singular deformations, they're not allowed in this space of deformations that we're considering, we can actually approximate them arbitrarily well by kind of very, very singular diffeomorphisms like this. So a consequence of that is if I look at the Hessian, so the second derivative of my energy functional, this tells me if I have a minimum or a saddle point, I want to calculate the Morse index of the Hessian. So what's the Morse index? It's the maximal dimension of a subspace where this Hessian is negative definite. If I look at the Morse index of the full Hessian, so on the space of all allowable deformations, or I look at the Hessian restricted to deformations that fix, say, the center point here, or even deformations that fix a small neighborhood of the center point, it turns out I get exactly the same Morse index in both cases. So even if I throw away all of the deformations that might move this point or do anything in a neighborhood of that, I can still recover the full Morse index. I can still explore all of the possible directions in my parameter space that might decrease energy, even though I'm not moving that singular point. And I'm not really going to talk about the proof of this. It's basically a kind of technical approximation argument. But I want to comment on it a little bit, because this is actually something that surprised us quite a bit when we discovered it. Okay, so there's a trivial inequality here that the Hessian on the full space of deformations has at least as many negative directions as its restriction to any smaller subspace. We just get that for free. But you might expect that this is actually a strict inequality. By throwing away a lot of the deformations, maybe we're missing some negative directions, some of the deformations that decrease energy. The fact that we actually have equality here depends on this approximation argument, which relies crucially on the fact that C0 infinity, smooth, compactly supported functions, are dense in the Sobolev space H1 half. More generally, these functions are dense in HS for any S less than or equal to 1/2. Right? For S less than or equal to 1/2, there's no well-defined trace map, boundary values don't really make sense, and there's no meaningful way of assigning zero boundary conditions. So 1/2 is exactly the threshold where that density result is true. On the other hand, what am I actually approximating here? I'm approximating things in the domain of the Hessian. So for this approximation to be useful, I need to know that the Hessian is actually continuous with respect to whatever norm I'm approximating in. And it turns out when you calculate the Hessian, we have explicit formulas for it, which I won't write down. The Hessian is continuous in any HS norm with S greater than or equal to 1/2. And so somehow we're exactly at the right threshold 1/2 where we can do this approximation argument and the Hessian is continuous. So we can do these very singular deformations or very singular approximations of deformations and still recover the full Morse index of the Hessian, seemingly without exploring a large subset of the parameter space. So again, it's a very, I don't know, it's very, we were surprised at first by this. So, you know, the fact that we're right at this threshold where we have continuity and density, it just works out perfectly somehow. Okay, so what are some consequences of this whole setup? So we have some K partition with corners, so everything is piecewise smooth. I'm assuming it's bipartite now. I'll get to the non-bipartite case in a minute. First thing we can show is that critical points of this energy functional are exactly nodal partitions of Laplacian eigenfunctions. That's an if and only if statement. Now, if you have such a critical partition, what is its Morse index? So that's telling you whether you have a minimum, a saddle point, or whatever. It's equal to n minus k. So n is the index or position of the eigenfunction that generates this partition. K is equal to the number of nodal domains. So remember, by Courant's theorem, which I wrote on the board over there, n minus k is always greater than or equal to 0. It's 0 exactly for a Courant-Sharp eigenfunction, where k is equal to n. It has the maximum allowable number of nodal domains. And so an immediate consequence then is if you have a Courant-Sharp eigenfunction, it gives you a critical point with Morse index 0 and vice versa. And so putting this all together, we get this really nice theorem telling us that a local minimum of this energy functional is the nodal, exactly the nodal partition of a Courant-Sharp eigenfunction is exactly a minimal partition in the global sense. So every local minimum is in fact a global minimum, which again is maybe surprising because, you know, this is a non-convex energy functional. It has lots of critical points, saddle points all over the place, but somehow every local minimum is going to be global as well. All right, and I should also mention, I mean, I should have written this on the slide, but this first theorem for bipartite partitions with corners, this generalizes an earlier result by Greg and his collaborators, Peter Kuchment and Uzi Smolansky, where they only dealt with generic partitions. So ones with smooth boundary sets coming from simple eigenfunctions of the Laplacian. So being able to deal with non-smooth nodal sets where we have intersections required quite a bit of analysis. That's kind of the main contribution of that theorem. And then it gives us these three equivalent conditions for minimality. Okay, so again, this is, so far I've only talked about the bipartite case, which is naturally tied to eigenfunctions of the Laplacian. What about the non-bipartite case? Well, we know these are not going to come from Laplacian eigenfunctions, just from unique continuation. And so what I'm going to do here is explain some other work we did where we defined a modified version of the Laplacian, which is also going to correspond to minimal partitions in kind of an analogous way. So we need to somehow generalize or modify our definition of the Laplacian to get an operator whose nodal partitions are not necessarily bipartite. What's going to happen in this case, as we'll see in a few minutes, I'll have this operator, we can talk about its eigenvalues and eigenfunctions and nodal partitions, And we'll see that nodal partitions for Courant-Sharp eigenfunctions of this modified operator are not necessarily going to be minimal partitions in the sense we had before, but they'll be minimal partitions at least within some topological class of partitions, which is what I wanted to find now. So to define this, first, I want to introduce the notion of what I'll call a piecewise C1 cut. You can just think of this as being the boundary set of one of my partitions with corners. So it's some finite set of C1 curves that intersect each other and the boundary transversely. So the first two pictures are good, third picture is bad because it has a cusp. So that's all I mean, just some finite set of curves that meet nicely. Now, given such a set gamma, I'm going to define this operator delta gamma, which I'll call the cut Laplacian, which acts like the Laplacian on kind of each component here, but I'm going to put anti-matching or anti-continuity conditions everywhere along this cut set gamma. Right, so if I just have this 4 partition, I want everything to be anti-continuous across each of these 4 pieces of the boundary, functions and their normal derivatives. This gives me a nice, well-defined self-adjoint operator, compact resolvent, so it's got eigenvalues and eigenvectors. A special case, if my cut set gamma is empty, then I'm not imposing anti-continuity conditions anywhere, and then I just recover the usual Laplacian. Okay, so that's this cut Laplacian, and the thing we need to understand is how does this depend on the choice of the cut set gamma? Other than the trivial case where gamma is empty, we just get the Laplacian. What if we had some gamma that looked like this? What would the corresponding operator be? So a simple observation, which is kind of a special case of a more general result that I'll present in a minute. If this cut set gamma happens to be the boundary set of a bipartite partition, then the corresponding cut Laplacian is unitarily equivalent to the regular Laplacian. The proof is very simple. It's basically shown in this picture here. Look at this cut set gamma. So it's just these 4 line segments. So it gives me this 4 partition of the square. It's bipartite. Now, if my function u, whose restrictions to the subdomains are just u1 through u4, if it's anti-continuous across each segment here, to produce a function that's continuous, on each segment, I should change the sign of u on one side, but not the other. And if I have a bipartite partition, that exactly allows me to do that consistently. So if I change u2 to minus u2, and likewise for u4, now across each of these 4 boundary components, I've changed the sign of u on exactly one side, and so all of my anti-continuity conditions have been turned into continuity conditions. So now I have some function which is continuous across the boundary. It's going to be in the domain of our regular Laplacian. And so this unitary transformation is just multiplying by -1 on every other domain in this partition. But again, to be able to do that consistently throughout the entire partition, we need some sort of coherency condition, which is exactly that the complement of this cut set is a bipartite partition. Okay, what if gamma is not coming from a bipartite partition? What if I just have some so I have the disk, and my cut set is these 3 line segments here, this Mercedes partition. Well, this is not the boundary set of anything bipartite, so the previous result doesn't apply. So the question is, how do I compare the Laplacian for this cut to other cut Laplacians? And so for that, we introduce this notion of homology of partitions, or maybe more accurately, homology of these cut sets gamma. So if I have 2 of these cuts gamma, so these piecewise C1 collections of curves, I'm going to say that they're homologous if their symmetric difference, or the closure of their symmetric difference, is the boundary set of a bipartite partition. This might kind of come out of nowhere, but we'll see some pictures on the next slide where we see how this actually arises in practice and how it's really closely related to the proof on the last slide of just changing sign on every other subdomain. Again, let's just take that as the definition of homologous cuts gamma 1 and gamma 2 for now. A special case, well, if I take, say, gamma 2 to be the empty set, then I'm saying gamma 1 is null homologous if and only if it's the boundary set of a bipartite partition. So P is bipartite if and only if its boundary set is null homologous. Now, what does this actually have to do with the normal idea of homology from algebraic topology? Well, remember, each one of these cuts is just the union of some collection of C1 curves. And so we can take that finite collection of C1 curves and view it as a singular one chain. So it's just some finite formal sum of curves in our surface. And it turns out if we view these cuts as one chains, then they're going to be homologous in this sense, if and only if the difference of these two one chains is identically zero in the following set. So viewed as an element of the first homology relative to the boundary with Z2 coefficients. So it is exactly homologous and in the usual singular homology sense, but we can also just think of it this way, which from the perspective of solving boundary value problems is much more natural. Okay, so here's a few examples to kind of show us what this definition is actually saying. So let's take the boundary set of this Mercedes star partition, these three segments, and compare it to these other cut sets, gamma 1, gamma 2, and gamma 3. So first one, I construct the symmetric difference. I get this. This is the boundary set of some bipartite 4 partition. So this gamma 1 is homologous to this blue set boundary of P by definition. The second case, gamma 2, again, I do the symmetric difference. Okay, take the closure as well, and I get this. Well, this is a bipartite 2 partition. So again, these two things are going to be homologous. But now if I look at this gamma 3, which looks almost the same, I've just shifted the intersection point down a little bit. Now I do the symmetric difference of these two sets. I get the following thing. Now I've got these triple intersections happening. This is no longer the boundary set of a bipartite partition. And so this gamma 3 is, according to our definition, is not homologous to the boundary set of the Mercedes star partition. So that's what this actually looks like in practice. Again, the point is you do the symmetric difference, take the closure, and then you just ask whether or not the resulting partition with that boundary set is bipartite or not. And it's going to be important because if it's bipartite, then we can construct some sort of unitary equivalence between these operators just by flipping signs on every other subdomain. So that's the following theorem, which includes the previous one as a special case. If I have two cuts, gamma 1 and gamma 2, that are homologous, their corresponding cut Laplacians are going to be unitarily equivalent. And the proof is basically this picture here. There's some technical details of gamma 1 and gamma 2 don't intersect nicely, but in the generic case where everything is transverse, this is what it looks like. So think about what we're doing. We have a function which is anti-continuous across this blue set, each of these three lines. We want to modify it to produce a function which is anti-continuous just across this red set. So I take the symmetric difference of these two things. It gives me this purple set here that's coming from some bipartite partition. Now I just flip the sign of U on one of the two components of that partition. Doesn't matter which, I've done it on the bottom one here. So U3 goes to minus U3. And now where before I had anti-continuity across this boundary, it becomes continuity. Similarly here, whereas on this red line, I haven't changed anything. And so my original function was anti-continuous, and it remains anti-continuous after this unitary transformation. So having homologous cut sets gives us this bipartite partition that allows us to construct this unitary transformation just by flipping signs, mapping from the domain of one operator into the other. So again, we now have this whole family of Laplacian-like operators. And what we see is, well, if lambda is null homologous, meaning if gamma is null homologous, so it's the boundary set of something bipartite, then we get an operator that is unitarily equivalent to the Laplacian. But in general, it's not going to be equivalent. Okay, so I've defined a bunch of stuff. What is the point of this? What do we actually get from all of this work? Well, we get the following theorem, so I'll tell you what it is in a minute after I've defined some terms. But basically, it tells us that Courant-Sharp eigenfunctions for this cut Laplacian minimize energy within a homology class. So I take some cut set gamma. I define this class of all K partitions whose boundary set isn't necessarily homologous to gamma, but at least contains something homologous to gamma. That's my pk of gamma. And then our theorem says, if I have a K partition coming from a Courant-Sharp eigenfunction of this cut Laplacian, then it minimizes energy compared to every partition in this class. Every partition whose boundary contains something homologous to gamma has to have energy at least as big as this nodal partition P that we started with. And it's important in this definition, again, that I'm requiring the boundary set of P not to be homologous to gamma, but just to have a subset homologous to gamma. So for instance, if gamma is null homologous, well, the boundary set of every partition contains a subset that's null homologous. Just pick the empty set. And so if gamma is null, then this is actually the set of all K partitions with no restrictions on their structure at all. On the other hand, if gamma is not null homologous, then this is actually a genuine condition, and this will be a proper subset of the set of all K partitions. So again, kind of summarizing this in words, Courant-Sharp eigenfunctions for this cut Laplacian give us partitions that minimize in the homology class determined by this cut set gamma. And in the special case where gamma is empty or is null homologous, we get the Courant-Sharp eigenfunctions for the Laplacian are minimal partitions. So we're covering this result of Helfer, Hoffman, Ostenhoff, and Terracini from 2009. So we recover that. We also generalize it to the non-bipartite case. And what we see here is that, I think this result, this notion of homology really clarifies what is so difficult about the non-bipartite case. Because, again, if gamma is the boundary set of a bipartite partition, then every other partition is in this homology class. So we can compare to everything. That gives us a global minimum. For a non-bipartite partition, we actually have some non-trivial topological condition. And so we can only compare to a subset of all partitions within some restricted topological class. Okay, maybe just a quick kind of simple example of this result. If we look at this Mercedes star partition, it's not hard to show that this is the nodal partition of a Courant-Sharp eigenfunction for this cut Laplacian, where we put our cuts on. You can do it on all three segments here, or just on one. They're unitarily equivalent, so it doesn't matter. It's Courant-Sharp for that operator, and so our theorem guarantees that it's minimal compared to all other three partitions in this homology class. And if you work through what that means, those are exactly the three partitions whose boundary set contains some curve from the origin to the boundary of the disk. So if the boundary set of any three partition contains some curve like this, then it's in this admissible topological class of partitions, and we can guarantee that it has energy greater than or equal to this Mercedes star partition. So these are the kind of results we can get from this homological construction. Okay, so maybe the last few minutes, I just want to kind of put together all of the pieces and then say a few words in closing. Okay, so what is the general idea or general picture here? We're talking about minimal partitions. So we have this partition of a domain or manifold into disjoint components, define this energy functional, and we've seen these three different notions of minimization. So global minimum, local minimum, and then this topological minimum within some homology class. And so the general result we get in the non-bipartite case, and sorry, this is a copy and paste error. This bipartite should not be there. So this is just any partition with corners. It's going to be a critical point of the energy functional with zero Morse index. So for instance, a local minimum. If and only if it's the nodal partition of a Courant-Sharp eigenfunction for one of these cut Laplacians, if and only if it's minimal within its homology class. So this is analogous to the result for bipartite partitions we had before. I just forgot to delete the word bipartite. So here we get being Courant-Sharp isn't necessarily equivalent to being a global minimum, but it is equivalent to being a minimum within the homology class. And again, for a non-bipartite partition, this homology class doesn't contain all other K partitions. It's a proper subset. And that's why this minimization problem is so much more difficult in the non-bipartite case. Okay, so just a few words in closing. Okay, so what did I hopefully show you today? Well, minimal partitions show up in lots of different mathematical and physical problems. They're very closely related to eigenfunctions of Laplacian, at least in the bipartite case. For the non-bipartite case, we need to somehow introduce new objects or new machinery like this cut Laplacian to get at minimal partitions. And this is a relatively new field. And so there are lots of really interesting open problems. I mean, I showed you early on, even rigorously determining the minimal three partitions of the disk and the square is not totally settled. So that should be the easiest possible problem to solve. And still nobody fully knows how to do that. And maybe one final open problem that I'll leave you with is something called the honeycomb conjecture, which basically describes the asymptotic behavior of minimal K partitions in the limit as K goes to infinity. So imagine you're doing a partition into more and more pieces, K is getting bigger and bigger. And basically this conjecture says that the minimal partition for large K is going to look more and more like a partition just into equal sized hexagons. So this kind of honeycomb lattice. Mathematical statement says if Lk of omega is the energy of the minimal K partition of omega, then the limit of this energy as K goes to infinity with some appropriate rescaling should just converge to the first eigenvalue or ground state energy of the unit area hexagon in the plane. So that's saying kind of tiling everything by hexagons should be the kind of asymptotic optimal partition in the large K limit. All right, so I think on that note, I'll stop there and thank you for your time. Okay, are there questions?
Yeah, I want to understand what you can do for this three partition. I mean, you have some partial result. I didn't quite understand what it was. So
yeah, so I mean, so the result we have in this case says, so this Mercedes star partition, it comes from a Courant-Sharp eigenfunction of this cut Laplacian we introduced. And so our theorem says that it minimizes energy within this homology class. So it minimizes energy compared to any other three partition that satisfies, some homological condition. What is that condition? In this case, it's exactly that the boundary set contains a curve from the origin to the boundary. So look at any three partition, look at the boundary set. If that boundary set contains such a curve from the origin to the boundary, then we can guarantee that its energy is greater than or equal to that of the Mercedes star partition. So that's exactly the homology class that we get in this case. And I mean, there's not really much to prove there, it follows from the general result, but basically the point here is if you look at H1 of the disk relative to its boundary, it's trivial. So yeah, if you take any two curves from the boundary to the center, those are going to be homologous. That's basically what it boils down to. So, so once you have all this machinery, you can kind of use like basic homological calculations to understand what this homology class of allowable partitions looks like. I mean, one thing that's kind of weird about this, and this is something we're still working on, right? The definition of homology that we introduced, which is just what arises naturally when you try to compare energies of these partitions and do this kind of sign changing construction. Right, so I'm saying it's a three partition whose boundary set contains a curve from the origin to the boundary. So in particular, it has to hit the origin, which is the singular point of this partition. And going back to this picture here, right? According to this definition of homology that we have, which I mean, again, it doesn't, agree with the algebraic topology definition when you view everything as singular chains. But in that definition, this gamma 3 is not homologous to the boundary set of P, which is, I mean, feels kind of weird because obviously one is just a small deformation of the other, but in the sense of homology that we need for our kind of min-max arguments to work, that does not count as homologous. So, understanding what happens, two partitions that have the same topology, three lines meeting at a point, not necessarily at the origin, that's still something that we need to understand better.
Well, so that wouldn't be included in your.
Well, yeah, so yes and no. This is. Okay, so this is not homologous to this. That's what this picture shows. However, this does contain a subset that is homologous.
Yeah, that's not enough though.
For our theorem, it is enough. So this is. But the thing is, even though we've moved the singular point down a little bit, this still contains a curve from the boundary to the origin. Yeah. That's what makes it work. If I perturb this to the left a little bit so it missed the origin, then we would be out of that class, which it feels like we should still be able to compare that, but we're not there yet. So it's kind of, it's a delicate thing. Other questions? Okay, so background again.